Thanks for the introduction. Yeah, so the original plan for this content was, it was originally written with the idea that Aurora would be online and that we could run through some interactive, kind of hands-on material. But that is, given that that is not the case, I've tried to make it, yeah, still as, applicable and generally relevant as possible. So, um, yeah, so as Khalid mentioned, I lead the models and pre-training team for the Aurora GPT effort. Um, so if for those of you who will be at the in-person session in a couple of weeks, I'll have a bit more to say on that then. But given that this is a hands-on section, I wanted to try to give some hands-on practical advice for how to scale training to, yeah, thousands of nodes and essentially across the entirety of Aurora. Um, I'll talk about later, but we have a recent result that, yeah, scaled to, I think, just over 98% of the machine. And so that was a pretty, yeah, big accomplishment and quite a feat to achieve. So just for some background, so I think, yeah, Filippo covered a little bit about distributed training earlier, and how to rep models with DDP. And so I'll kind of go a bit quickly, maybe through um, the kind of logic behind distributed data parallelism and just kind of dive right into some hands-on examples. But the basic idea behind distributed training or scaling your training run is to minimize the amount of time spent training, whether that be the cost spent on renting GPUs or really just the cost of running on GPUs in general, right? You want to minimize that cost. And so you can cut down on that cost by using more GPUs, right? By doubling the amount of GPUs I'm running across, I can cut the amount of time I have to spend training typically in half. And so how do you go from training on a single device to training on the entire supercomputer? So typically, if you are just running on a single GPU and training a relatively small, simple model, your setup looks something like this. So you take as input a single batch of data at a time, feed it forward through your network, get out some loss value, backpropagate the weight updates to your network, and update them. Oh no. Give me 1 second. Turn on do not disturb so I don't keep getting pinged. So yeah, as I was saying, your setup typically looks something like this, right? Where you work through your data a single batch at a time, going iteratively, computing a loss, updating your weights. And if you want to go from a situation like that to training on multiple GPUs, typically what you do is employ what's called data parallelism. And so in this approach, what is done is the data is fed simultaneously to unique GPUs, or unique batches of data are fed simultaneously to different GPUs. So you can see in this example, instead of working through my data iteratively batch at a time, I instead feed multiple batches to different GPUs simultaneously. So GPU, for example, gets this batch 0, same with GPU 1 and 2. They each compute their local loss and perform a gradient averaging. So everybody syncs up after doing the forward step, calculates the average weight update to update, and sends that averaged weight back out to the network so that at each step, all of my GPUs have identical copies of the network. And so continuing in this manner, you're able to get through your data much more quickly, and allows you to, yeah, really kind of make better use of the resources available. So yeah, that's just basically what I just said before, right? So after the forward step, all of my workers have their local values of their loss. There's some global all reduce happening where they average their gradients across all of the workers. Those updates are then synced and then sent back out to each of the networks so that they all maintain identical copies at each step. So this is now a relatively common practice, and there are a lot of existing libraries that can help you get started and require minor modifications to existing code. So if you have a model that you can currently train on a single GPU, it's relatively painless to go from training on a single GPU to training in a distributed data parallel fashion on multiple GPUs. There, yeah, it is now it's natively built into PyTorch through this distributed data parallelism library. There are also external libraries such as Hugging Face's Accelerate and Microsoft's DeepSpeed that both offer a handful of different other additional features besides simple data parallelism, but yeah, they just kind of have different trade-offs and have different, features and things that make them attractive. But for the most basic setup, the idea is really pretty simple, and really could be implemented by hand and if need be. But fortunately, there are a lot of libraries that have done it for you, so you can take what they've done and just kind of plug it into your existing code. So there are a few things that are kind of driving this behind the scenes that are what are actually important when you want to talk about performance. So as I mentioned previously, at the, you know, towards the end of each training step, there's this global averaging of the gradients that happens across all of your workers. And so in order for this operation to proceed successfully, all of my workers or every rank in my MPI job must participate. So that requires syncing up globally between every single GPU. Depending on the amount of GPUs you have, that can be a non-trivial task, right? Like if you're running on 98% of Aurora, that's 10,000 nodes or roughly 120,000 GPUs. And so if you need 120,000 GPUs all to be able to talk to each other, yeah, the implementation of your collective algorithm and performance of your collective algorithms becomes increasingly important. And there are, I think, as mentioned previously in the context of Aurora, Intel has their one API collective communications library, and that's what powers collective communications on Aurora. Similarly, NVIDIA has their own collective communication library called Nickel, and AMD similarly has their own for their hardware named it's actually named Brickle, RCCL. I left the L off the abbreviation. Right, but these are the actual implementations that drive the collective operations that can be interfaced through your favorite MPI binding in Python. So MPI for Py, PyTorch distributed, so on and so on. But these are really essentially API calls into the underlying collective implementations. What happens unfortunately very commonly at very large scales is that it is often the case that one maybe isolated individual GPU might be straggling a bit behind all of the rest of your workers. And so if you have even a single GPU that is running, even a few, I don't know, hundreds of milliseconds behind, that can cause a whole slew of errors in your networking and collective communications. And so when it's really important in all of this that your collective communications libraries are well optimized and well tested, because your training can really only proceed as quickly as your slowest GPU. And so really making sure that all of them proceed in, a lockstep fashion is actually very important for getting all the performance you can when running at scale. So there are a few kind of subtle things to be important or to be aware of that are actually important when doing this in practice. So like I mentioned earlier, at each individual training step, you need to be sure that each of your workers is being fed a unique batch of data. So sentence data parallel, you want each worker to always be working on a unique batch of data, which is, kind of sounds obvious, but you need to be somewhat careful in the implementation. And then another important thing is that you typically only want to perform file IO from one single worker. Typically that's rank 0. Or at least you don't want to have multiple ranks trying to read or write from the same file, because this can lead to race conditions and cause unexpected behavior. And typically just, something that you want to avoid. So you want to, whenever possible, or yeah, whenever you really need to write to or write to or read from a file, you want to be careful that you're not having multiple workers all trying to access the same file at the same time. Essentially, because that can lead to locks and these race conditions and essentially just cause undefined behavior. This is actually, so this is comes up in practice specifically when you're trying to restart training and load from a checkpoint, for example. So typically what is done is you will have a single GPU read in the saved checkpoint, and then once that GPU has read in the checkpoint, you typically then broadcast the model and optimizer states out to everyone so that you avoid all of them trying to read from the same file at the same time. So these are just a kind of a couple other general recommendations, best practices. So you can effectively hide the cost of communication behind insufficiently compute intensive workloads. It is possible to hide the cost of the communication behind the computation. And so this, in some sense, depends on the level on how well developed the communications libraries are. So for example, it's a little bit easier to do on an NVIDIA CUDA-based system at the time, for the time being than it is on Intel. But that's something that's very much under active development and making progress forward. So that's one of the large one of the things you can do that can have a large impact on your model performance. So effectively hiding communication behind computation is one of the big tricks that you can do to really improve performance. Using parallel files, file stores, file systems, so HDF5 parallel, and yeah, parallel MPI/IO in general for parallel file operations can be useful depending on the amount of data you have to read or write. So there are things like data striping on Lustre, although given the performance of Lustre recently, that's really up for debate. And so on. So there are a bunch of different tricks that you can do to try to really kind of squeeze out the last little bits of performance. But yeah, at that point, really, if your model is running well at large scale, yeah, the best thing to do is typically actually profile the code and figure out where it's actually spending the bulk of the time and try to optimize things sort of that way. And so that's kind of in a nutshell all there is to say about distributed data parallel training. If you have more GPUs available, you can typically just scale to more GPUs and get through your training more quickly. And yeah, that's kind of a very popular paradigm for distributed training. But unfortunately, if you try to continue following that approach, eventually you will hit some wall, right? So if you could just scale along the data parallel dimension forever, that would be great, but unfortunately you can't. And what really happens in practice is that typically you will want to scale your model beyond what is available in GPU memory. And so what, is a probably more reasonable plan of attack or strategy in general for scaling to larger model sizes across and larger GPU counts is this kind of flowchart I made. So this is not meant to be definitive by any means, but just kind of a rough heuristic for how to proceed, right? So if your model is perfect and it does as well as it can, and you're happy with the quality of it and it can't do any better, then you're kind of done, right? There's nothing else to do. But in the real world, your models are not perfect and there's always room for improvement. And so typically, no, your model is not perfect. And so if your model is not perfect, the next step would be to make it larger, right? And so you can just make it larger and larger until eventually you run out of GPU memory. And once you eventually run out of GPU memory, you can't make your model any larger, right? Because you can only have a model as large as can fit in GPU memory. And so what do you do then? You kind of have to resort to a different approach or kind of employ some different strategies. The most straightforward or simplest probably being zero offloading, which is a feature in Microsoft's DeepSpeed. Or additionally, you can resort to additional parallelism strategies like tensor parallelism, or activation checkpointing, which isn't a parallelism strategy, but is just another technique for offloading memory during training. And so there are a couple other kind of tricks you can do that don't rely on employing an additional parallelism strategy, so like zero offloading or activation checkpointing. But typically, if you really want to scale up to real large model sizes, you will eventually hit a point where you most likely need to employ some sort of model or tensor parallelism. And so, yeah, this is what I was basically just saying, right? So when the model does not fit in a single GPU, you can employ some of these offloading tricks. So deep speed plus zero offloading is useful for freeing up memory, actually, is very useful. Nowadays, PyTorch has their own native implementation called FSDP that can actually be very effective at freeing up GPU memory at the cost of reduced throughput. So there's this kind of nice diagram from Microsoft DeepSpeed that illustrates how the different zero offloading strategies behave. And so what's typical, oh, you guys can't see that, can you? So typically when you are training in a normal distributed data parallel scheme, and you have identical copies of your model on all of your GPUs, your situation looks something like this baseline case, right? So on each one of my GPUs, I have identical copies of my model, optimizer states, and gradient weights. And this is duplicated or kind of replicated on each one of my GPUs, right? GPU 0 has all of this information, GPU 1 has all of this information, and so on. But in some sense, that's kind of redundant, right? Because at each GPU only needs to worry about its own local copy of the optimizer states for the backward step, right? So the easiest case is 0 stage 1, which just offloads the optimizer states. And so in this case, each model or each GPU retains the entire copy of the model and gradient information, but only retains its own kind of local copy of the optimizer states. And so in doing that, it frees up, a significant amount of memory on each device at the cost of having to kind of get the missing information at runtime from all of the rest of the GPUs. So this is very advantageous if you want to free up GPU memory, but obviously, like I said, comes at the cost of decreasing model throughput, right? Because instead of just doing the backward step with weights that I have locally, I instead need to get all of the missing information from all of my neighbors first. Once I've reconstructed that information, I can then do the rest of the backward step. And so by increasing the zero offloading stage, you can free up additional, kind of GPU memories in increasing fashion, right? So the first stage offloads just the optimizer states. The second stage offloads the gradient and optimizer states. And then in 0 stage 3, it offloads all of them. So the model parameters, gradients, and the optimizer states. And so this obviously frees up 0 stage 3, frees up the most memory, but comes at the cost of the most reduced throughput. And so these are, like I mentioned, useful if you want to scale up, just by a little bit, or the model size that you ultimately want, maybe it happens to fit in memory with 0 stage 3. And then in that case, right, you kind of don't have to worry about it and you're good to go. But what's typically the case is that you want to scale your model to even larger sizes, right? And so eventually this offloading strategy kind of hits a wall. And eventually, if you want to, continue to scale your model to larger sizes, you'll eventually have to resort to some sort of additional parallelism strategy. And so there are, yeah, anything that is not data parallel is kind of is frequently grouped in as being just called tensor or model parallelism. But there are actually kind of subtle differences between these different approaches. But they often kind of just get grouped under the category of like model or tensor parallelism. So yeah, what's typically thought of as tensor or model parallelism involves actually distributing the weights for individual layers across multiple GPUs and is probably the most complicated to implement. Is kind of requires a lot of manual splitting up of weights and sharding of things, and so it's probably the most tedious to do in practice. Pipeline parallelism is a bit easier and has nowadays there's even some built-in support in DeepSpeed and PyTorch for pipeline parallelism. Same with sequence parallelism. So this kind of applies the parallelism over the sequence dimension or over the context window. And so they're increasingly more that yeah, these days there are more and more libraries that will attempt to do these parallelisms for you automatically. Um, I would say it's still in the pretty early stages of development, and so oftentimes what you'll see when people need to resort to these kind of tensor or model parallelism strategies is that they will do it themselves, which is obviously error prone and, as I mentioned, tedious, and just much more complicated and involved than standard, you know, data parallel training. To give a maybe some better intuition to how these actually function. So pipeline parallelism is maybe the easiest to get, to kind of wrap your head around. So in this case, you essentially split the model up vertically over multiple GPUs. So you can imagine if you had four layers that you wanted to run in pipeline parallel over two GPUs, you could imagine splitting them up something like this, where the first two layers live on GPU 0 and the last two layers live on GPU 1. And so then in order to do a full forward pass of your network, you need to feed the data into GPU 0. It goes through layer 0, output to, intermediate through layer 1. The output from layer 1 would need to be sent then from GPU 0 to GPU 1. And then it can, proceed through the rest of the layers, so on and so on. And then similarly for the backward propagation, right? You just back propagate as you would in the reverse order that you went through in the forward step. And so it kind of requires, like I mentioned, there are nowadays a lot, DeepSpeed and PyTorch have, I believe, built-in support for native or for, kind of simple, naive pipeline parallelism. But it's, yeah, not too complicated to implement if you needed to by hand, right? You just need to be somewhat careful about how you send data at the boundaries between GPUs. Tensor parallel is like I mentioned, probably the more involved or complicated example. So in this case, individual layers are split between GPUs. So you can imagine in this case, instead of a layer residing entirely on a GPU, half of it would lie on GPU 0 and maybe half of it lies on GPU 1. And so in order to, you know, get to the next layer, you need to very carefully split your data, send the parts that need to go over here, over there, and the parts that need to go over here, get their outputs, send them through the next layer, and so on and so on. But yeah, so you can kind of imagine, right? Hopefully, just from me explaining this, that's a bit more complicated. And if you were to want to implement that yourself, you would need to be a bit more careful in how things are split up, for example. Yeah, so there are a few now increasingly more and more libraries that will try to do this automatically for you, or that will try to like remove all of the possible pain points from you having to do it yourself. And so that's good, obviously, because it's challenging to do and do well. So being able to build off of existing libraries is advantageous. I would say they're still pretty early in yeah, these are pretty new libraries. So Nanotron is relatively new. There's also a new library from PyTorch called Torch Titan, um, that can do some of this for you. But yeah, they are still, I would say, pretty early in the development stage for most of them. To give maybe a concrete example and just maybe give a bit more of an applied example for how you would actually do this in practice. So this is maybe like the simplest tensor parallel example you could think of. So I want to just compute the sum of, inputs multiplied by weights, but imagine that the weights are all isolated on separate devices. So in this case, for example, say weight 0 lies on GPU 0, weight 1 on GPU 1, and weight 2 on GPU 2. And I want to compute the sum over xi times each of those weights. And so in order to do this full calculation, you need to first send x0 into GPU 0 or into GPU 0 and compute that first product. Once I've gotten that, I can then send that output to GPU 1 and as well as the input that I need to calculate that term. So take in x1 and the output from that first calculation, add those two terms together, send that output to GPU 2, do the same thing, take the x2 input, multiply it by its weight, and add that to the rest of the terms. And only then, once I've done all of those steps, can I, really assemble the output of the calculation. And so this is, yeah, maybe, yeah, probably, one of the simplest examples you could kind of dream up. And even trying to think about how you would do this and, in an automated fashion for large networks is pretty non-trivial, I would say. So, yeah, so those are kind of the main ideas I wanted to get through. Maybe kind of the next like section is going to be, next I'm going to talk a bit high level about some recent results that we've, yeah, achieved for scaling throughput on different machines and Aurora specifically. And then depending on time, I'll try to walk through maybe a couple of quick examples that the code is all there for and that people can run, at their own leisure whenever the machines are back online. But I'll at least point people to it and kind of give everybody an idea of how to like run it once they are able to. But before I get into that, any questions on any of what I've said so far? I saw there have been like a lot and the chat has just been going off and I didn't respond. So Khalid, I think I saw you replying, so thank you.
Yes, I tried to answer as many as I could.
Beautiful. Yeah, and also I'll double check at the end too. Also, so yeah, I see a lot of questions about Aurora GPT. Yeah, so we'll talk more about that at the in-person week. And if people are interested more in Aurora GPT specifically, I've got a bunch, yeah, if you look at my website, a bunch of other talks that talk a bit more specifically on that. And so feel free to look through those as well. But yeah, this being the hands-on, I wanted to try to give a bit more hands-on material, hopefully. So no questions then? Beautiful. All right. So yeah, next briefly, I just want to talk a little bit about some of the results that we've achieved over the past year or so now on a few different machines. So the first is this are the results from this mprot DPO effort that is led by Arvind Ramanathan, who is a scientist here at Argonne, that was employed this direct preference optimization training paradigm in an effort to design protein sequences. And it was a finalist last year for the Gordon Bell Award at Supercomputing. And there's a link to the full paper here, so if people are interested. But I'm mostly, for now, interested in talking about the scaling performance. So Yeah, this was last year's Gordon Bell finalist, and we were really proud of it. So we got a little over 4 exaflops of sustained throughput training at 3,200 nodes of Aurora, which is just over 38,000 XPU devices. So I don't remember exactly what the number was, but it was just over 4 exaflops, which, was a tremendous effort and, um, yeah, really, hard fought number, honestly, I would say. So that was, a really big achievement, and we're really happy to see that. So this is using MIT's Precision BF16. One of the nice things about this paper and this result is that we were able to run it on a bunch of different systems. So the code for all of this natively runs on Intel devices, CUDA devices, or AMD devices. Um, and so we were able to get results from a few different machines. So Aurora, obviously being Intel, ALPS is an NVIDIA-based system. I think these are all NVIDIA based. We have results in the paper with the 7 billion parameter model that have results on Frontier, which is an AMD based system. But at any rate, the point being that this result was one of the nice things about this effort and this result is that it was very portable. And so ran out of the box on all of these different accelerators. And so we were able to get, pretty good throughput on all of these different supercomputers across the world. And so it's a really, yeah, really huge effort from the team and a really big accomplishment, I would say, all around. And so that, like I said, that was last year's supercomputing HCM Gordon Bell finalist. This year, actually, we just announced. I think the publication, the archive went up last week, I believe. But we have another finalist this year for the climate track specifically. And so it's on this Aries model, which is a diffusion transformer model for climate and for weather forecasting in short, and seasonal to subseasonal, weather forecasting. And so yeah, we got even better performance this time around. So, for this result in the scaling of this climate model, Aries, we were able to achieve just a little over 10 exaflops on 10,000 nodes of Aurora. So that ends up being about 120,000 XPU devices. Um, yeah, and which is, so I don't know if Vaino is here. I don't think so. But so he really led this effort and really drove the, scaling front on this for this work. And so it was, yeah, again, another very hard fought number. But we were very happy with these numbers and very, excited to see these sorts of scaling results. And so there's a bunch of other very interesting details in the archive preprint that's up now. And so I encourage people to go and look there if they're interested or have more questions. Um, yeah, so this is, like I mentioned, very recent. So it is a finalist for the Climate Gordon Bell this year at Supercomputing. So we will know, yeah, the awards are announced on at Supercomputing. So here in November, a couple months, we'll know. But yeah, at any rate, it was a very the model itself, beyond just the scaling numbers, is competitive with GenCast actually, and so does very, very well at actual weather forecasting and has a whole bunch of other very interesting science details and results in the paper. So I really do encourage people to go look at that if they're interested. Um, so with the last 10 minutes, I was going to try to talk at a somewhat high level about this library that I've written and maintained called Easy Peasy. That yeah is has kind of actually been somewhat of the driving force, and the underlying portability framework for these recent Gordon Bell efforts. So in essence, it's a library that allows you to abstract away hardware specific PyTorch details. Um, so easiest way to see this maybe would be if you have some code currently um, that runs in DDP or distributed any sort of data parallel fashion, you will probably have some in there you will have some calls to torch.distributed.init process group. And then depending on the hardware you're on, so if you're on an NVIDIA system, you'd need to init that process group with the nickel backend. If you're on XPU, you'd need to use the XCCL backend and so on. And so the first thing I did was to abstract away those details. So instead of having to worry about the distributed backend being used when you call that init process group, you can just call this easy peasy setup torch, which automatically initializes all of the GPUs in your available in the runtime. And so you don't need to worry about which backend I'm using and so on. The other maybe most useful quality of life improvement is that if, for example, your code is currently written to run on CUDA-based machines or CUDA systems, NVIDIA-based systems, you will typically have a lot of these model.2 CUDA calls lying around. And so if you were to then want to run your application on Aurora, for example, you would need to manually go in, find all the CUDA calls, swap it out with XPU, so on and so on. Which nowadays is not. So there's been a lot of development from Intel and PyTorch to get native support for XPU in PyTorch. And it's in a much better state now than it was maybe, I don't know, 2 years ago or so when I started working on this. But at the time, yeah, this was, I would say, maybe a bit more involved. And the idea of having an accelerator agnostic interface was, yeah, less concrete. And so nowadays I think even in PyTorch, in the newer versions of PyTorch, there are things like automatic device selection in that. But at any rate, I still, yeah, like my like my library, and there are a few other additional features that I also think are useful. Um, One of the most useful probably being um, this ability to automatically launch distributed processes. So um, this easy peasy test call. So if you are in a Python environment that has PyTorch and MPI for Py installed, all you need to do is install this easy peasy library. Once you have it installed, you can then run this easy peasy test, which will just launch a very simple distributed test on all of the resources available. So this is kind of scheduler aware. So it will automatically figure out the details of your PBS or Slurm job. So for example, it'll calculate or it'll figure out the number of GPUs available on each node, as well as the total number of available nodes. Use that information to build the appropriate srun or MPI exec command, depending on the scheduler. And then, build all of that as necessary and then actually execute it. So you kind of have this generic ability to launch Python processes from Python directly, without having to manually specify details about like, how many GPUs I have and so on and so on. And so that's kind of nice in my opinion. Um, yeah, it being my own personal library, there are a bunch of other things that I've kind of added that are useful to me, and that other people have seemed to generally kind of appreciated. So there's, for example, a distributed debugger. So you can call, if you have some distributed code that is buggy or crashing, you can kind of just wrap it in this easy, try except loop, and catch the exception with this breakpoint on a single rank, which is kind of nice. Yeah, I've got things like automatic experiment tracking. So if you use weights and biases, which I do a lot, you can kind of just build this history object and it'll automatically keep track of it. Um, we have 4 minutes left. I suppose I should probably wrap up. So I've got it here toward the end, this kind of very minimal example that kind of shows all of these ideas all in one. That, yeah, I would encourage people to go through and run once the machines are back online. Yeah, and if anybody, runs into any issues or has any additional questions, then feel free. I'm, very reachable, happy to talk at any time, definitely about anything related to this. And so, yeah, I would really encourage people to go in and work through the examples, and kind of let me know how it goes. Any problems or questions show up, obviously feel free to let me know. There's also some links. Yes, so there are also some links. So the GitHub repository is online, obviously. I gave I gave another talk on Easy Peasy, maybe in a bit more detail at the Insight Hackathon earlier this year. And so there are slides from that here as well that people might be interested in. There's also a documentation page that I know could be better, and I'm working on improving actually. But it's there, and so it kind of has some coverage for the Python API. So yeah, you can go and look at that and see the actual source code if you want. Yeah, there are a whole bunch of other kind of nice features that I need to document and put up here, but if this is something that is of interest to any of you, yeah, I would really encourage you to reach out, because I definitely would welcome, yeah, ideas into how to make it better or things that people think might be useful. Yeah, I'd be happy to talk more about. So I think that's about all I have time for.